So in previous sessions, we've talked about some of the properties of star evolution and star life cycles. We talked about star formation, where a giant molecular cloud will form a cluster of stars, going through the protostar phase, and eventually, once they are fusing hydrogen into helium in their cores and have gravitational equilibrium, we get these main sequence stars. And we talked about, in a previous session, the evolution of low-mass stars, going from a red giant to a planetary nebula and eventually leaving behind a white dwarf. What we want to do in this session is talk about high-mass stars, where the main sequence star is more than around 8 solar masses. You'll probably notice that for low-mass star, we said less than 2 solar masses, and now for high-mass stars, we're saying more than 8 solar masses. There is a bit of a gap in there where we can kind of be in between these two phases. It's not a clear straight line delineation. So we're going to kind of break it into these two more well-defined categories than they actually are. Again, there are intermediate mass stars that are doing things kind of in between these two. So let's talk about these higher mass main sequence stars. So when they're main sequence stars, even though they're higher mass, they still have the property of main sequence stars. They're still in gravitational equilibrium. They're still fusing hydrogen into helium in their cores with this same overall reaction. 4 hydrogen nuclei going in, turning into 1 helium nuclei, plus a lot of energy, neutrinos, things like that. But the cores of these stars, the cores of these high mass main sequence stars, they're going to be at much higher temperatures, densities, higher core fusion rates than the lower mass stars that we've looked at. And at these higher masses, at these higher temperatures and higher densities, there's actually another version of hydrogen fusion that's more efficient at these high temperatures than the proton-proton chain that we talked about for low mass main sequence stars. We said that low-mass main sequence stars are powered by hydrogen fusion via the proton-proton chain. In these high-mass stars, sorry, this should be fusing. In these high-mass stars, this is going to be via something called the CNO cycle. So what is this CNO cycle? This is a set of nuclear reactions where carbon, nitrogen, and oxygen are used as a catalyst for hydrogen fusion. The overall reaction is still 4 hydrogen nuclei going in, 1 helium nuclei coming out, plus energy and a bunch of neutrinos. But at these higher temperatures and densities, carbon, nitrogen, and oxygen, again, act as catalysts to speed up the reaction. The carbon, nitrogen, and oxygen don't get used up in this reaction. They don't get produced by this reaction. They're just catalysts that allow the reaction to occur significantly more efficiently than the proton-proton chain. So again, in these high-mass stars, for the main sequence high-mass stars, they're still powered by hydrogen fusion, but it's using this CNO cycle rather than the proton-proton chain. These high-mass main sequence stars, they're fusing hydrogen into helium in their cores, but they're still going to run into the same problem that our low-mass stars ran into. Eventually, the core is going to run out of hydrogen. So when the core runs out of hydrogen, it's going to turn into a supergiant. In this new phase, the star's size changes quite significantly. The surface temperature goes down, the outer layers kind of puff outwards. A lot of these initial steps are very, very similar to what was happening in those low-mass stars. In the low-mass stars, we said, okay, the core runs out of hydrogen and starts to collapse. And then fusion starts in a shell around that inert helium core. And that runaway shell fusion puffs up the outer layers of the star. making it larger. Eventually, helium starts fusing in the core. That temporarily supports the star again. And then the core runs out of helium. We get a helium fusing shell, hydrogen fusing shell, basically the same sort of steps that we went through for the low mass stars. So make sure you kind of revisit those. But for these high mass stars, the difference is these high mass stars in their cores, it's going to reach temperatures, pressures, and densities that are going to be sufficient to fuse elements heavier than carbon. So we get similar stages to the low mass stars. But can fuse heavier elements. So those steps that we talked about for the low mass stars, the core runs out of a fusion element, starts to contract. We get a shell of fusion burning that element in an outer, in a shell around the core. And then the next heavier element starts to fuse inside and repeat that. We're actually going to be repeating this for elements heavier than carbon. This is powered by something called helium capture reactions. Again, whenever we're talking about these different star phases, one of the things that I do want to emphasize is how is energy generated in each of these different phases. So for supergiants, it's powered by helium capture reactions. And there are a whole host of these kinds of helium capture reactions. For example, if I have carbon, carbon-12, that has 6 protons and 6 neutrons, and I fuse it with a helium nucleus, 2 protons and 2 neutrons, I'm going to make oxygen, 8 protons and 8 neutrons. Eventually, the core runs out of carbon, and we're going to start fusing oxygen in the core. Oxygen plus helium is going to make neon. Eventually, I run out of oxygen. We've got neon plus helium. Well, that's going to start making magnesium. And in each of these reactions, we make a new element that has an atomic number 2 larger than the previous element. We have carbon, atomic number 6. Add helium, atomic number 2. We get oxygen, atomic number 8. Oxygen, 8, plus helium, 2, gives neon, 10, and so forth. So each reaction, we get a new element that is 2 larger in atomic number. So let me back this up for a second. These helium capture reactions, each element atomic number is plus 2 larger. Now, we've been going over a lot of information about how different reactions occur inside of stars, different things about the life cycles of stars. And as we hopefully are all aware, when I make a particular claim, the response should always be, well, what is your evidence for this? Well, by looking at different clouds of dust and gas in space, we can look at what is the abundance of elements in different parts of the galaxy, in our galaxy. This table is going to be very, very important for understanding how we know what we do about the fusion reactions going on in these different stars. Okay. So what this graph is looking at is the relative number of atoms in each element. So if I'm at this point on the graph, then I have 100 times as many atoms of this material as if I were at this point on the graph. So notice that this scale goes up by powers of 10. So this would be if, we have some reference element here. Beryllium is used as the reference element. This would say I have 100 times as many of this element than I do beryllium. This is 1,000 times, or sorry, 10,000 times more. This is 1,000,000 times more, 100 million times more, going all the way up the scale. So again, this scale is very, very dramatically increasing as you go higher on the scale. And on the horizontal axis, we have what is the atomic number? Basically, which element on the periodic table are we looking at? We've got hydrogen is the first element, helium is the second, lithium, beryllium, boron, carbon, nitrogen, oxygen, all the way up the periodic table. And there are a lot of key properties about this graph that we are going to want to focus on. First one you might ask is, well, what are the most common elements in the universe? So have a look at the graph and try to answer that, maybe pause the video. Which elements are the most common in the universe? Well, that's going to be our hydrogen and helium. We said that hydrogen and helium in most of the materials that we're talking about, stars, clouds of dust and gas in space, it's about 3/4 hydrogen, 1/4 helium. And all the rest of this graph is the 2% of other stuff. And this hydrogen and helium was originally produced in the Big Bang. What about all these other elements? Where did these other elements come from? Well, if we look at this part of the graph, you'll notice that the abundance of elements kind of jumps up and down. We get quite a bit of carbon, not as much nitrogen. Quite a bit of oxygen, not as much fluorine. Quite a bit of neon, not as much sodium. We get this kind of bouncing up and down pattern. And what we find are elements with even numbers, even atomic numbers, are much more abundant than elements that have odd atomic numbers. And the reason for this is these helium capture reactions. These helium capture reactions, we said they tend to produce new nuclei with an atomic number too larger than the previous one. So this is going to produce, we've got some carbon, we're going to be able to easily produce oxygen. We've got oxygen now, we're going to be able to easily produce neon. We've got some neon, we're going to be easily able to produce magnesium, but we are not as easily going to be able to produce those odd numbered atomic elements. So we can look at the abundance of elements in the universe and track that to which elements are produced in these certain types of nuclear reactions. Notice also on this graph that lithium, beryllium, and boron, atomic numbers 3, 4, and 5, are really low down. The reason for this is fusion in stars, we said hydrogen fuses into helium, and then we said that helium will undergo that triple alpha process where 3 helium nuclei come together to form 1 carbon atom. So again, that's why lithium, beryllium, and boron are not significantly produced in stars. The triple alpha process skips these. This graph, again, is going to be pretty important. Hint, hint, make sure you're studying it. Because it tells us a lot of information of how we are literally made up of star stuff. Remember, the hydrogen helium was the material that was, produced in the Big Bang. What are the other elements that are common in our bodies? Well, oxygen, H2O, it's one of the main things that makes up our body. So oxygen is super prevalent in our bodies. Carbon, also super prevalent in our bodies. We are carbon-based life forms. Some of them aren't as prevalent, like neon isn't very prevalent in us because it doesn't interact chemically. But if you take these abundance of elements that are produced in stars and weight them slightly according to how chemically active are they, again, things like neon, helium, they don't interact chemically, so they just don't show up in the human body. But basically, all of these other elements follow the exact same patterns as the abundance in us. We are literally made out of exploded star remains. So again, in these supergiants, we're getting these increasingly massive nuclei forming the core through helium capture. And that process of the core runs out of some sort of material and starts to compress. We get a fusing shell around that core, and the next element is fusing inside. Supergiants just take this to a ridiculous extreme. So, for example, most of the outer layers of the star are still just ordinary unreacting hydrogen helium. But then we've got a hydrogen fusing shell, a helium fusing shell, a carbon fusing shell, an oxygen fusing shell. And as we go further and further into the star, we get more and more heavy elements. And in each of these stages, the core compresses, heats up, and runs through its remaining fuel faster. So we get this layering of fusing shells with heavier elements fusing further in, deeper in. Fuses hotter and faster. And faster at each step. And again, this just keeps on continuing through, other materials. Again, these aren't the only reactions that are going on in the stars, but these are going to be the dominant ones. And eventually, we build up heavier and heavier elements until we get to iron in the core. When we get to iron in the core of this supergiant, we run into a very, very serious problem. Iron is the most, iron 56 specifically, is the most stable atomic nucleus. So we get to iron, the most stable nucleus. And that's a problem because if we want to generate thermal pressure via a fusion reaction or via some kind of nuclear reaction, with iron, that's a problem because if it is stable, it will not give up any energy through a nuclear reaction. So being the most stable atomic nucleus, when you're trying to go through fusion, is a real problem because this yields the least energy of any nuclear reaction. Iron does not want to go through nuclear reactions. If I try to break iron apart through fission, it doesn't give off energy. If I try to fuse something to that iron nucleus, it's going to be less stable. It's not going to give off energy. So those fusion reactions of heavier and heavier elements that were staving off the death of this star, when we get to iron, that is the end of the line. So neither of these reactions are going to work. And once the iron core forms, computer models suggest that the star would have less than 1 day. So no energy via fusion, no energy output via fusion, via nuclear reaction. So the star's about to die. Okay. And again, each of these reactions, earlier on, when I said that each of these reactions are compressing the core, heating up, and runs through its fuel faster, these high mass main sequence stars, they might fuse hydrogen in their core for a few tens of millions of years, maybe 100 million years or something like that, depending on the mass. It might run through the helium in the core in 1 million years or less. It might run through the next element, fusing carbon, in a few tens of thousands of years. And each stage, it gets shorter and shorter and fuses through those materials faster and faster. Once we get to that iron core, we've got about one more day. What's going to happen after that one more day? Well, if we look at this diagram, we're going from supergiant to something that doesn't look very pretty for the star. This is a before and after picture taken 10 days apart of a star that has gone through the supernova. This is kind of like the easiest possible spot the difference question that you've ever seen. The star before and what it looks like 10 days after during this supernova event. So this iron core is going to lead to a supernova. These are extremely violent events. When we talked about low mass main sequence stars and saying we've got a red giant that is continually puffing up its outer layers, and eventually those outer layers get puffed up so much that they're just ejected from the star as a planetary nebula, those are still violent, but relatively gentle compared to these supernovas. We've detected these from, very, very quite distant past. For example, there was a supernova that went off in the year 1054 AD. And we know this by reports from astronomers from China, India, the Middle East, a couple other locations, where basically a new star showed up in the sky. So this is a report. I have observed the appearance of a guest star. On this star, there was a slightly iridescent yellow color. This thing was so bright, this star could be seen during the day for a couple of months. There are cave paintings in New Mexico that date to 900 to 1100 AD. There are paintings in these caves that may be actually referring to this Crab Nebula, this new star appearing in the sky. That one we're a little bit less sure of. And now we actually know where the leftover exploded remnants of that star are. This is a picture from I think this is a Hubble image of the Crab Nebula. And we can confirm that this is the leftover exploded remains of supernova 1054. We can observe how fast those exploded remains are moving away from the source. And if I know how fast those are moving, and I know how far they've moved, we can basically mathematically rewind the clock and figure out when this thing exploded. And that was in the year 1054. This is an image of supernova 1987A. Let me zoom in on this a little bit. Supernova 1987A is the nearest recent in terms of while we've had advanced telescopes that we've actually detected. We see these supernovas going off all the time in very distant galaxies, but this supernova went off in a galaxy that's right next door neighbor to the Milky Way galaxy. And these are follow-up Hubble images of that supernova that went off in 1987. The shock wave from that supernova is expanding and running into previously expelled gas clouds, causing them to light up in these different colors. So there were other layers of the star that were more gently kind of ejected away, but then when this thing exploded as a supernova, that shock wave eventually hits that material and causes it to light up. In large galaxies like the Milky Way galaxy, we expect these supernovas to happen every 100 years or every couple hundred of years. We're actually overdue for one occurring in the Milky Way galaxy. A little bit overdue, just kind of based on how often these occur. But even if these only occur every couple hundred years in a large-sized galaxy like our Milky Way, we monitor many, many thousands of galaxies, and there are specific programs to detect when these supernovas go off in distant galaxies, and we see these happen, most nights. We see a lot of examples of these kinds of supernovas. Even if something is rare, if you're observing a lot of cases, even if something is generally rare, you're going to see lots of instances if you're looking at a large enough number, a large enough sample. So what's actually happening in this supernova event? There's a couple of very important steps that are going on. So let's talk about these supernovas. We've got this iron core that's building up, and that electron degeneracy pressure supporting it against collapse. Again, we've got, so that iron core supported by electron degeneracy. We've talked about this a couple of times already. It's that property where electrons don't like being in the same quantum state. And this material is so compact and so dense that those electrons, since those electrons don't want to be in the same quantum state, they actually provide some pressure. And this will eventually fail. So that iron core was building up, was temporarily supporting itself, but eventually that electron degeneracy pressure is going to fail. And we're going to get a new reaction. The reaction that we're going to get is that electrons plus a proton produces a neutron plus a neutrino. And in this reaction, the neutrinos actually carry away the vast majority of the energy produced in this reaction. For every proton that's in this iron core, when it fuses with an electron, it's going to give a neutrino away. A neutrino is going to fly off of this thing in absolutely tremendous quantities. This reaction occurs extremely quickly. Because let's think about this reaction. We're taking a proton and electron, and we're fusing them together to make a neutron and a neutrino. Well, the thing that was supporting the stars against collapse was this electron degeneracy pressure. The electrons were the only thing stopping the thing from just collapsing immediately. And now we're removing the electrons. So as soon as this thing starts to collapse, it removes the electrons that were, stopping this thing from going through further collapse. And it's like pulling the rug out from under it. Just imagine you're on a chair or something, you're standing on a chair, and someone pulls the chair out from under you. There's nothing that stops this thing from collapsing almost instantaneously. So what's going to happen? So when these electrons and protons combine, that electron degeneracy pressure disappears entirely. It was supporting this massive gravitational forces, these massive gravitational forces pulling on this object, trying to compress the core. All of those are just gone. All of the forces resisting that are just gone. That core will collapse into something we call the neutron star before the outer layers of the star even notice what's going on. So this thing collapses into a neutron star. The outer layers, even going at the speed of light, the speed of light travel time is too slow for the outer layers of this star to even notice what's going on. It really kind of reminds me of those old Roadrunner and Wile E. Coyote things where the coyote accidentally steps out over a cliff and doesn't even realize that there's a cliff below him and then just plummets down immediately. So this iron core has violently collapsed in the course of a few milliseconds into a neutron star. And a ridiculous number of neutrinos have been produced. Remember, for every proton that was in this iron core, we're going to produce a neutrino. These are going to be numbers like 10, somewhere around 10 to the 56 or 10 to the 57. A 1 followed by 56 or 57 zeros. That many neutrinos. we talked about neutrinos and how they pass through most material. If I fire a high energy neutrino at the Earth, it will make it almost all the way through it'll make it through the Earth most of the time without noticing anything. But these neutrinos, even though most of those neutrinos can escape, the tiny percentage of neutrinos that are actually absorbed by the outer layers, it carries so much energy that those outer layers of the star get launched off the star at around 10% the speed of light. So these neutrons, the tiny percent of neutrons that get absorbed by these kind of intervening layers, they launch those intervening layers out, and that slams in to the very outer layers of the star, producing this massively energetic shock wave. So neutrinos, the neutrino basically blast off the outer layers of the star. And again, most of the energy in the supernova is actually carried away freely by those neutrinos. The massive shock wave that's produced in the exploding star that we can actually see, detect easily, that's just a tiny percent of that neutrino energy. So this is a phenomenally large amount of energy being produced in here. But these neutrinos blast off the star's outer layers, and that creates a shock wave. A shock wave off the star. That shock wave, well, that actually produces its own temperatures and densities that are much higher than even we had before in the cores of these very large stars. And we get this process called neutron bombardment, where I've just got some atomic nuclei over here, but this shock wave that's coming in, there are so many neutrons flying through this material that we can actually produce much, much heavier elements. So neutron bombardment in the shock wave produces elements heavier than iron. So elements heavier than iron are actually produced during these supernova events. We now know that there are other kinds of interactions that also produce these heavy elements, things like two neutron stars running into each other. We'll talk about some of these kinds of events a little bit later, but this is one of the ways that elements heavier than iron are actually produced. So if you look at a periodic table, again, the hydrogen and the helium was mostly produced originally in the Big Bang. Lithium, beryllium, and boron those are produced by cosmic rays. We're not going to talk about that in too much detail. Small stars can produce a bit of carbon, nitrogen, oxygen, maybe a couple others for those kind of intermediate mass stars. Large stars produce most of the elements up to iron. There are some additional ones that it produces as well. But most of the elements heavier than iron are actually produced in these supernova explosions. So if you have, say, the nickel in a nickel, like the coin, that nickel was likely produced in the intense shock waves produced in these supernova events. Same if you have gold, or if you have some, what are some other things, like silver partly, tin partly, lead. All of these elements are produced in these extremely energetic events, things like massive star supernovas, or if I have things like neutron stars running into each other, that will also produce these kind of conditions with this strong neutron bombardment, producing these heavier elements. Going back to this graph, we can see that even if I consider the general downward trend in the abundance of these elements, if I consider that general downward trend, we're still getting a bit of a drop when we get these heavier and heavier elements. So after iron, again, it's the most stable one. So if you produce iron, it's going to be sticking around quite a bit. That's part of why it has a bit of a jump up here. After iron, there's a significant drop in the abundance of these heavier elements. And the reason for that is because, well, these supernovas are not all that common. These are more energetic events. So we have this lower proportion of these heavy elements. So again, this graph is going to be an important piece of information. There are questions that are going to be on the homework, possibly on the next test. So again, make sure you're being careful with how you're using this graph. This is not a stellar spectrum. This is looking specifically at how much of each type of element do we see for different kinds of elements. We talked about how hydrogen and helium is produced in the Big Bang. Helium gets converted to carbon, skipping some of these through that triple alpha process. Even numbered atomic nuclei are more common than odd numbered due to those helium capture reactions. And these heavier elements are not super common because they're only produced in these supernova events. After this supernova, these ejected materials, well, they are now enriched with many of these different kinds of heavy elements. And that ejected material is eventually going to mix back into new clouds of dust and gas, new giant molecular clouds. And they will enrich those new giant molecular clouds with these heavier elements, with the heavier elements that were produced in this, during the star's lifetime and during this supernova event. Eventually, if they cool off, well, eventually they're going to be primed for forming new generations of stars that now have some of those heavy elements. And again, our solar system, when it formed, the cloud of dust had already been seeded with heavy elements by these kinds of events. And now, when our sun forms, around the sun, we have the right kind of materials to make a rocky planet like the Earth, and eventually the right materials to eventually have conditions where life can start. We are literally made up of these kinds of exploded star guts. What's going to be left behind by these supernova events? Well, it depends on what is the mass of the core that was left behind. If the mass of the core is between around 1.4 solar masses and 3 solar masses, you're going to get this neutron star. Basically, when those electrons and protons fuse together, they made neutrons and neutrinos. The neutrinos fly away, blasting away those outer layers of the star. The neutrons are left behind, and if the remaining core isn't more than 3 times the mass of the sun, well, you just have this giant ball of neutrons left over. And notice that the majority of the mass of the star actually was blasted away during that supernova event. We said for typical high mass stars, we're going to start that at like 8 solar masses when it's a main sequence star. Most of those solar masses of material were blown away in the supernova event. But if the core is even more massive, then we might get a black hole where there's so much mass in such a small space that there is no known physical force that can stop that from collapsing all the way down into a black hole. So in some of the next sessions, we'll talk about the properties of these different kinds of leftover dead stars, white dwarfs, neutron stars, and black holes. We'll be talking about some of those different kinds of dead stars in some of the next sessions.